In this capsule, we will move away from the stability of carbanions into the discussion about the stability of carbocations. So here are the main topics that we'll discuss in 2 or 3 capsules. We'll start with the types of carbons and then we'll move on to types of carbocations and their hybridization, bond angles, so on. And in the next one, we'll go into the factors that actually impact the stability of carbocations. Resonance is one of them. We've done a few problems with anions, but resonance can also be seen in carbocations. There's another one which you were familiar with before. We called that negative inductive effect. Here we're talking about a positive inductive effect. And then there's something called hyperconjugation. So this is the broad topics we look at as we deal with the stability of carbocations. So with that, let's talk about the types of carbons in a chain. So we have seen some chains, small chains with some of them are just straight chains, some of them have branches. So I'll draw a few structures on the board first. So let's take a look at a carbon like this, a compound, pentane. And now I'll just move on, draw a couple more structures there, and then one more. Okay, so I have 3 structures. We're not looking into naming. We can do the naming too, simply just to get into practice. So we have 5 carbon alkane, so this is pentane, and 1, 2, 3, 4, 5. So we have 2 methyl pentane, and here we have 1, 2, 3, 4, 5. So we have 3, 3 dimethyl pentane. That's naming, and that's not what we're talking about here. But just because we wrote the structures, I gave you the names. But we want to develop a system where we can talk about carbons slightly differently. So I want to erase this so we can see what we need to slightly better. So in structure 1, pentane, you have 2 methyl groups, 2 CH3s on either end. So you have the 2 CH3s here. That's a CH3, this is CH3, and then all these are CH2s. There is a CH2, a CH2, a CH2. So here we develop a terminology. Okay, the CH3 carbon, you see it is connected to just one more carbon. The carbon, CH3 carbon, is connected to just one more carbon. So the CH3 carbon is called a primary carbon. Now, likewise, this CH3 on the other end, this CH3 here is also a primary carbon. And because we want to simplify everything, we just denote primary carbon like that. Okay. So so in pentane, this molecule, pentane, you have 2 primary carbons. Okay. And then you have this CH2s. Let's take a look at the CH2s. Okay. Let's start with this carbon here. That carbon, this carbon is connected to 2 other carbons. So such carbons are called secondary carbons. Okay. That's a secondary carbon, which we denote it in simplified fashion as that. So a secondary So likewise, you see the central carbon here. The central carbon is also connected to two carbons, one on either side. So that is also a secondary carbon. And finally, this carbon here is another secondary carbon. So pentane has two primary carbons and three secondary carbons. This is just to develop a system of calling them. So do not confuse naming, systematic naming with this classification. They are two different things. Now, let's move on to the next structure, 2-methylpentane there. So just for space and for clarity, I will erase the first one so we can just draw them a bit larger. I'll remove this and remove the entire other two also, and then draw them again as needed. So 2-methylpentane. Now here, let's just number them first. So carbon 1 there, and let's call this carbon 6, carbon 5 and carbon 6. Carbons 1, 5 and 6 are connected to just one other carbon, directly connected to. So an important point there. Carbon 1 is directly connected to directly. So to just C2. C2 is connected to C3 and all that, but carbon 1 is connected to C2. And C2 is connected to everything else, but we are just focused on this, C1 to C2. Likewise, C6 is also connected to just one other carbon, which happens to be C2. Carbon 5 is directly connected to carbon 4. So carbons 1, 6 and 5, since they are connected to just one other carbon, are all primary carbons. So carbon 1 is a primary carbon. Carbon 6 is a primary carbon. Carbon 5 is also a primary carbon. And just do primary carbon. Now, we have seen secondary carbons too in the previous example. So let's see if carbon 3 and 4, let's look at carbon 3 and 4. Carbon 3 is connected to carbon 2 and carbon 4. So carbon 3 is connected to two carbons. So that is a secondary carbon. Carbon 4 is connected to carbon 3 and carbon 5. So that is also a secondary carbon. Now, this one more carbon that's remaining. Carbon 2, you see carbon 2 is connected to carbon 2 is connected to carbon 3, carbon 1 and carbon 6. Carbon 2 is connected to three other carbons. So that is a tertiary carbon. So now we have carbons can be classified as primary, secondary and tertiary carbons. Let's draw one more structure and then move on from there. So, the last structure that I drew on the board previously was this one. Okay. So in this, again, let's number them just for the sake of convenience. Carbon 6, carbon 7. So in this one, let's see, carbon 1, carbon 5, carbon 6, carbon 7. All of them are directly connected to just one other carbon. So C1 is connected to C2 directly, C7 is connected to C3 directly, C6 same C3, C5 is connected to C4. So carbons 1, 6, 7, 5, no order, just calling them carbons, are all primary carbons. What about carbons 2 and carbon 4? Carbon 2 and carbon 4 are directly connected to two other carbons. So carbon 2 is to 3 and 1, 4 to 5 and 3. So carbons 2 and 4 or secondary carbons. Whereas carbon 3, that is connected to 4 different carbons. So that is a quaternary carbon. Carbon 3 is connected to 4 different carbons. It is a quaternary carbon. And so primary carbons, secondary carbons, tertiary carbons, and quaternary carbons. These are the 4 types of carbons you can see in any molecule, and this works on sp3 hybridized carbons. Notice all the structures that we are looking at, we are just looking at sp3 hybridized carbons, so not sp2 nor sp. Okay, so this is types of carbons, and based on this we'll get carbocations. So you can have primary carbocation, secondary carbocation, and tertiary carbocation, which we'll look at in the next capsule. So here, the small, just enough information that we need to talk about the carbocation, the types of carbocations. Okay. Now, one type of problem that you can see here is, based on this type of the information that is provided here, let's say a problem can appear like this. Draw the structure. Remember, we had constitutional isomers. So many different types of structures can be, written for a given molecule. So let's say I have the molecular formula is C5H12, and I want you to draw a unique structure with this provided with this information. Draw a structure. Of course, you can draw a structure like this, right? But yeah, it's correct. But in this particular question, what I'm asking is, draw a structure, constitutional isomer for this molecular formula that has only primary hydrogens, primary hydrogens. So, oh, that reminds me to just say something else. So, we are talking about primary carbons, right? So these are carbons. Carbons are classified as primary, secondary, tertiary, quaternary. So are hydrogens. So hydrogens is simply the hydrogens on a primary carbon are primary hydrogens. Hydrogens on the secondary carbon are secondary hydrogens. And then likewise we have a tertiary hydrogen, and of course we will not have any hydrogens on a quaternary atom, because what is quaternary? Quaternary is a carbon. Quaternary carbon is a carbon that's connected to 4 other carbons. So there's no hydrogen on that. So now combine these two. So draw a structure, draw a constitutional isomer of C5H12 that has only primary hydrogens. Okay? That means hydrogens on a primary carbon. What is the primary carbon? A carbon connected to just one other carbon. A primary carbon is a carbon connected to just one other carbon. Primary hydrogens are the hydrogens that are on the primary carbon. So that means there are 12 hydrogens in this molecule, right? C5H12, and we want to draw a structure in which all of them, all 12 hydrogens are primary hydrogens. That means all 12 hydrogens must be in the form of methyl groups. So we have 4 methyl groups, CH3, 4 methyl groups. So we have 4 carbons in 4 methyl groups. We have the 12 hydrogens. At this point, if you pause and look at the molecular formula is 5 carbons. So there's one other carbon there. One other carbon. So how do we connect all these bits of information? We got 4 CH3s. How did we get this 4 CH3s? Because the information that was given to us is draw a structure that has only primary hydrogens. What are primary hydrogens? Hydrogens on a primary carbon. What's a primary carbon? Carbon connected to just one other carbon. Okay. So if you draw, so let's complete this thought here. So we have this information, and you know, you cannot connect one CH3 to another CH3. You cannot do any more there, and that's not the complement we are looking for. So you cannot draw that. There's this one carbon sitting there, you know, we need to account for. So put the carbon there, and then put the 4 CH3s surrounding that central carbon. So you came up with the structure. So that is the structure, that constitution. So we are looking for that particular constitution isomer. See, there are 4 methyl groups: primary carbon, primary carbon, primary carbon, primary carbon, quaternary carbon. Okay? And all 12 hydrogens are primary hydrogens. So that is the structure, that specific structure we are looking for in this particular question. Okay? So you cannot draw structures like this, because if you draw a structure like this, there are 2 methyl groups that are primary. That's a primary carbon, that's a primary carbon. So you have 6 hydrogens, 6 primary hydrogens, but then you have this here, 3 CH2s, you have 6 secondary hydrogens. So that's not what we're looking for in this. Right. So let's stop here, and in the next capsule we'll look at the different types of carbocations.